Hello everyone. So today we are looking at how much change occurs over time in the carbon and water cycles. So we need to look at the two cycles and we need to look at things that cause them to change. So do you remember this concept of dynamic equilibrium? Hopefully you can remember this from coasts, where we talked about dynamic equilibrium in terms of sediment in equaling sediment out on the beach. And we talked about the fact that there had to be some sort of natural feedback going on within that system in order to restore that equilibrium. So the summer constructive waves were building up the sediment on the beach, which in turn was increasing the gradient. And then we had that switch to the winter destructive waves, where the backwash is stronger than the swash because the gradient of beach has caused that to happen, and therefore that extra sediment is removed from the beach and we maintain that equilibrium in that way. And most natural systems, if they're unaffected by humans, will exist in a state of dynamic equilibrium. So we've got continuous inputs, we've got movement throughout the system and outputs, and variable stores of energy and materials. And we see fluctuations from year to year, but ultimately in the long term, we see a balance. We see this equilibrium within the systems. So thinking about our feedback loops that occur, a few people have got a bit confused with these on test 2. And I know why you've got confused, because the terminology is confusing. So when we talk about negative feedback loops, we're not talking about something negative happening. I can see why you would think that's the case, but a negative feedback loop is actually restoring equilibrium. So perhaps one way to think of it is that a negative feedback mechanism, that negative feedback is taking away or minusing the part of the system that started to get out of control. And so it's taking away that negative thing that's happened in order to restore equilibrium again. So negative feedback systems restore balance. They bring back that dynamic equilibrium. The positive feedback systems are the ones that spiral out of control, and something negative happens, which means something else negative happens, and it gets worse and worse. So you are plussing to that negative, you're adding to that negative and making it worse. So within a drainage basin, when we have lots of rainfall, when we have heavy rainfall, that will increase the amount of water stored in the aquifers. So the level of water beneath the ground starts to rise. The water table rises. And then what happens in order to restore equilibrium there is the springs either side of the water table will then release that extra water into the rivers and revert that level of water beneath the ground back to normal. So remember, these springs are where the water comes out through the banks of the river, and this is where your Evian water and all those different waters that you like to drink in your bottles are supposedly bottled. So there we've got a negative feedback loop. Those springs are releasing the extra water and returning the water beneath the ground to an equilibrium. In the carbon cycle, this is quite an interesting thing to think about long term. So when we talk about burning fossil fuels, we tend to focus on the real negatives of that. Too many fossil fuels in the atmosphere will trap the heat and will cause our climate to warm up greatly, and that's going to be a really bad thing. But on a long-term scale, if we've got more carbon dioxide in the atmosphere, then that is going to stimulate photosynthesis. And if we've got more plants growing in a warmer climate, in the northern part of the world, the southern part of the world, for example, then actually that extra carbon dioxide in the atmosphere stimulating photosynthesis means that there's more carbon being taken in by the biosphere, by the plants. And that extra photosynthesis will remove the excess CO2 from the atmosphere and restore equilibrium. So if we're thinking of all sort of doom and gloom at the moment about what's going to happen with climate change due to the greenhouse effect, thinking on a longer term scale, lots of people are pointing out that the fact that this extra photosynthesis that will be stimulating could well, in the long term, restore equilibrium to the carbon cycle. So let's have a look at what humans are doing that impacts the water cycle. So land use changes. So the first one on here is looking at urbanisation. So fairly obviously, if we take an area of rural land and we turn it into an urban area, like you can see in those two pictures there, we are changing that surface. We're taking a permeable surface, and with all that concrete and tarmac, we are leaving an impermeable surface. There's no longer the infiltration that there used to be. There's far greater surface runoff, and as a result, the hydrograph, do you remember that lesson on hydrograph, will become more flashy. The lag time will decrease, the peak discharge will increase, and the risk of flooding will be far greater. So when you take a rural area and you make it urban, so urbanisation, this can massively change the flows within the water cycle. Farming also impacts the water cycle. So when we change the vegetation, when we change the soil, so if we have an area of forest and we deforest it and we turn it into farmland, we are massively reducing the amount of carbon that is stored both above and below the ground in terms of biomass. But also when you plough a field, you churn up the soil, you expose that soil to the atmosphere, and oxidation can occur, which will also reduce the carbon storage of the soil. And then if you think about the natural system, when we talk about the rainforest and we talk about nutrient cycling, we're talking about dead leaves falling to the ground, putting nutrients back into the soil. When we farm the land, we clear the whole field. We don't leave behind any residue. We don't leave behind the leaves and roots to put that organic matter back into the soil again. And then also where you've got land that's been farmed over and over again, that can make the soil very brittle, and it can easily be washed away by the wind and washed away by the water as well, which then reduces the actual soil content on the ground. Farming also impacts the water cycle. So we irrigate the grounds. In some parts of the world, they recreate tropical conditions in areas that are semi-arid. We're using a huge amount of water from storage and putting it onto the soil, onto the ground. And that then impacts the flows of water within the water cycle. And you've got a huge amount of extra evaporation that's taking place. You've got a huge amount of extra interception and infiltration that you wouldn't have had without humans putting that huge volume of water. And down the bottom left there in that picture, you can see a sprinkler system. That's the kind of thing I'm talking about. That is not natural water coming into the system. That is humans simulating what would happen in the rainforest in terms of the amount of rainfall. Ploughing, like you can see down the bottom right hand picture there, also increases evaporation. So when you create these furrows, so like the lines that have been created by that plough, they act as drainage channels. They massively increase the rate of runoff and the rate of soil that's washed away. So that can be a big impact on the water cycle. And then also where you've got lots of tractors and combine harvesters and heavy machinery going up and down the fields, that can compact the soil so that you then get flows of water straight across the surface much faster. Forestry also changes the water cycle. When we have a natural forest, we tend to have much higher rates of interception. We tend to plant conifers in the UK if we're going to plant a new forest. And these are the evergreen trees, the Christmas trees, if you like. And we tend to plant them quite close together, which can lead to very high interception rates. Because we've got so much interception, we've then got increased evaporation, that water going straight back into the atmosphere. We've got reduced runoff. There's less water reaching the ground. And that can then increase the lag time, reduce the peak discharge on the hydrograph, which reduces flood risk, but also means there's less water for the public to use in those areas. We also tend to see higher rates of transpiration from these kind of forests than we would from farmland or moorland, which are the kind of ground we tend to be planting forests on. And then you also get a very rapid temporary change to the water cycle when you harvest the trees. So if you've got a Christmas tree forest that's there for most of the year, but during December you chop down the trees because people want them as Christmas trees, suddenly you've massively reduced your interception. You've taken away, you've had a very temporary but very significant impact on the water cycle. And suddenly you've got increased runoff, you've got reduced evapotranspiration, and you've got much more water going into the rivers as discharge. In terms of the carbon cycle, when we change land from farmland to forest, we're increasing the amount of carbon stored, obviously, in the trunk and in the roots and in the branches of the trees. So if you look in the UK, a mature forest tree has 10 times the tons of carbon per hectare than grassland, and 20 times the carbon per hectare than an area of heathland. And those trees are taking CO2 in from the atmosphere through photosynthesis and storing it for hundreds of years. However, trees only become an active carbon sink for the first 100 years after they're planted. Once they reach the age of 100, the amount of carbon that they're taking in levels off. And as a consequence, a lot of these forestry plantations usually have a rotation period of 80 to 100 years. So they're chopping down the trees on that kind of time scale and planting new ones to restore that carbon sink. And then humans are obviously extracting water as well to use it for public, to use it for industry, to use it for agriculture. So for example, the River Kennet here, which is in Wiltshire and Berkshire in southern England, you've got a picture there that shows you where it is and the drainage basin itself. It's a chalk upper catchment, so you've got lots of water being stored beneath the surface. There's loads of wildlife supported by this river because the chalk filters the water and makes it really, really high in oxygen, and it's perfect for lots of different creatures like the Atlantic salmon, the brown trouts, you've got the water voles, you've got those white-clawed crayfish, which is the bottom picture there, for example. There are also some pretty big urban areas around the River Kennet. So Swindon, for example, has got a population of more than 200,000, as well as industries and agriculture. And Thames Water also takes water from the upper River Kennet catchment. So this has had a significant impact on the regional water cycle where we're taking water out. And if you look at that picture there, that was back in 2003, but you can see that River Kennet sign. Well, where is the river? It's not there. It's bone dry. It's completely and utterly dried up. During 2003, we had a huge fall in river levels, for example. And where you've got a situation where humans are extracting more water than is being recharged through rainfall. So we're taking more water out of those systems than is coming in as rain. then we get a situation where we're decreasing that store of water. That then has a big impact on the wildlife that depends on that river, as well as the humans that depend on that water. So do you remember aquifers? These are the store of water in the rocks beneath the ground, an underground reservoir of water, if you like. Now you need certain geography for an aquifer to form. You need this permeable rock beneath the ground. You need the kind of rock that is going to act as a sponge and store the water. But you also need an impermeable layer beneath that permeable layer. So in that diagram on the left, the blue section is the aquifer, but beneath that we've got impermeable ground. We need that because we need to stop the water infiltrating down into the ground below. We want to trap the water between two areas of impermeable rock. And what we do then is we dig a borehole down into the aquifer and we extract that water and we use it for people, for industry, for agriculture. So this is an artesian basin, and this is where you have got a situation where you've got this sort of semicircle of permeable rock which comes to the surface at either end, and on top of it and below it you've got impermeable rock. And what happens is when it rains, the rainwater goes in where you've got those recharge areas. So if I can just work out how to get a little pen here. So when it rains here, that rainwater goes down into the ground and also on this side as well. So when it rains, the rainwater can infiltrate into the permeable ground at those 2 points. And then it fills up the permeable rock layer, that semicircle of blue that we've got here, this area here. I'm not very good at drawing with my mouth. So this is our store of water. This is our aquifer, this semicircle here. And because we've got impermeable rock above it and below it, that then puts that water under pressure. And so all we need to do is to dig a well, dig a borehole down into that artesian aquifer, and the pressure will just send that water up to us. And we're able to really easily extract it. And there's a little YouTube clip that you can watch here that will show you that in more detail. And actually London is located on top of an artesian basin. You can see that we've got a chalk aquifer trapped between impermeable London clay and Gault clay. And that rainwater is entering that aquifer in the North Downs and in the Chilterns, way outside on the outskirts of London, and then making its way and filling up that permeable artesian basin beneath the city. And then we just dig our borehole down and we can extract that water under pressure. And groundwater from the chalk is an important source of water for London. However, we have seen some pretty big changes in our use of water. So during the 19th century, the first half of the 20th century, we were using a huge amount of water from beneath London in that artesian basin for all of the industry that we had in London, and we were over-exploiting it. However, as deindustrialisation has occurred and industry has left London to be replaced by tertiary and quaternary industries, we've seen a massive reduction in the amount of water we've needed in London. And we've started to see since the 90s a rise in the water table. And that was pretty bad for the underground, because the underground had been built at a time where we were using that water massively for the industry in London. And then as we've declined in our use of water, the water levels have started to threaten those underground tunnels. And they've had to take some pretty drastic action to extract the water to stop it from flooding the underground tunnels themselves. And you can watch this clip. It is a bit old, this clip, but you could get the idea from it, to show how this has threatened the underground system, our reduction in water extraction in London. Okay, so these are the questions that I'd like you to answer. Make sure you've got some really good notes. I really don't mind how you do your notes, whether you want to answer these specific questions or you just want to make notes from throughout the lesson. You just need to make sure that you've got a really good coverage of everything that we've talked about today. Any questions, let me know.